Differentiation is a method used to compute the rate change of the function f(x) with respect to its input s. This rate of change is known as the derivative of f with respect to x.
There are 6 techniques of differentiation. First, derivative of constant, linear and power. Second, derivative of sum and differences. Third, product rule. Next, derivative of trigonometric, exponential and logarithmic function. The fifth one is chain rule, and last but not least, quotient rule. We should find dy over dx for the following function, which is y equal to 3x squared secant x plus 2. So firstly, let u equal to 3x squared and v equal to secant x plus 2. Next, I differentiate u, which give u prime equals to 6x. After that, I differentiate v equal to secant x plus 2 using the chain rule. The derivative of secant x plus 2 is secant x plus 2 tangent x plus 2. Then I apply the product rule, which is dy over dx equal to u prime v plus uv prime. It will be 6x secant x plus 2 plus 3x squared secant x plus 2 tangent x plus 2. Therefore, the final answer is dy over dx equal to 6x secant x plus 2 plus 3x squared secant x plus 2 tangent x plus 2.
For the question B asked to find dy over dx for the given function y equal to 4x plus 2 over cos x. Looking at this function, we can see that it's a fraction. Therefore, to find the derivative, we must use the quotient rule. Let's define our u and v component from our function. U equal to 4x plus 2, v equal to cos x, u prime equal to 4, v prime equal to negative sin x. Now, we substitute by into our quotient rule formula. Let's simplify. The first term is simply for cos x. For the second term, we have a minus sign multiplied by another negative sign from negative sin x. This changes the operation to a plus sign. We can factor out a 2 from the 4x plus 2 term if we want to make it look clear. Or we can expand it. This is a final simplified derivative of the function.
For question number 3, these are the question and how to solve it. First of all, we need to separate into 3 to make it more easier to solve each part of the question. For the first part, we will declare y ln 3x as number 1, e power of 2x plus 1 as number 2, and 10 for y as number 3. First, for y ln 3x, we will use product rules because the number is multiplication. We will let u equals to y and v equals to dy dx. Then, we will differentiate u, so we will get dy over dx. When we want to differentiate y, we must put dy dx. After that, we will differentiate v. So, we will get 1 over s after we factorize it. Now we move to number 2, which e the power of 2x plus 1. We will differentiate this equation, which power we differentiate, and we will multiply it in front of the e. That equals to 1, and we'll get 2e the power of 2x plus 1. For number 3, 10 for y, the formula to differentiate 10 is secant the power of 2x. For y is x. Then we will put our equation inside the formula and it will be secant the power of 2 and 4y. Then we will differentiate 4y and it will turn out 4 secant the power of 2 4y dy over dx. Now we combine this result back into one equation. Our next task is to isolate all terms containing dy dx on this one side. Factor out dy dx from the left side and now simply divide to solve for dy dx. Finally, to clean up the expression, multiply the numerator and denominator by x.
Hello everyone, today we are going to look at question 4, which asks us to use linear approximation to estimate the value of this expression. The 4 roots of 80.99 minus 2 over the square root of 80.99, correct to 3 decimal places. First of all, we need to define our function f(x) by replacing our messy number at t.99 with the variable x. So we will get fx is equal to fourth root of x minus 2 over square root of x. To make it easier to differentiate, we need to rewrite the root as fractional exponents. This gives us fx equal to x power of 1 over 4 minus 2x power of negative 1 over 2. Next, we find the derivative f prime x using the power rule. Differentiating the first term gives us 1 over 4x minus power of negative 3 over 4. For the second term, we bring down the negative 1 over 2, which cancel out the negative 2 and change the sign to a plus, giving us positive x power of negative 3 over 2. And then we rewrite this back into fraction form for easy calculation. And our derivatives is f prime x equal to 1 over 4x power of 3 over 4 plus 1 over x power of 3 over 2. Now, we need to choose our target point x and a nearby nice point x0, where the value are easy to calculate without a calculator. Our target x is at t.99. The perfect number close to this is 81, because 81 is a perfect fourth power, especially 3 power of 4 is equal to 81. So we set x not equal to 81. Next, we need to find out the delta x. The delta x have a formula which is x is minus 2x naught equal to at t.99 minus 81, and we will get the delta x is negative 0.01. Secondly, with our point established, let's evaluate both our original function and our derivative at our chosen base point at t1. For the function f at t1, the first root of 81 is 3 and the square root of 81 is 9. Doing the maths gives us 25 over 9, which is approximately 2.07778. For the derivative f prime at t1, plugging 81 into our derivative formula and simplifying gives us a very precise fraction equal to 31 over 2916. Finally, we bring it all together using the linear approximation formula, which is fx equal to fx naught plus f prime x naught multiplied by delta x. Substitution our values into the formula, we have 25 over 9 plus 31 over 2916 multiply negative 0.01, and the final answer is 2.7778. And as a question want us to get the 3 decimal places, so we only get the final answer is 2.778. In conclusion, differentiation is a fundamental technique in calculus that is used to determine the rate at which a function changes with respect to a variable. Through various differentiation rules, such as the power rule, product rule, quotient rule, and chain rule, complex functions can be analyzed efficiently and accurately. This technique plays an important role in solving real-world problems involving motion, economics, and science by helping to identify rates of change, maximum and minimum values. Overall, differentiation provides a powerful mathematical tool for understanding and modeling dynamic relationships in both theoretical and practical applications.